In the name of the Father, and the Son, and the Holy Ghost. Amen. All right, so we're going to look at some discontinuities today. So our objective, identify discontinuities from a graph and distinguish between removable and non-removable continuity, okay? So remember, for a function to be continuous, three things have to be true, and I basically boiled it down to this. The limit as x approaches a from the left has to equal the limit as x approaches a from the right, and that all has to be equal to the function value at a particular place. Now, the limit has to exist for this to work, so if f of a is undefined, or if the limit doesn't exist, then this is all bunk, right? It doesn't work, okay? So, again, the limit as x approaches a from the right has to be equal to the limit as x approaches a from the left, and then it has to be equal to f of a, okay? So, we can do some review. Is f continuous at x equals 0? Well, the limit as x approaches 0 from the right, we're going to use this function. So 9 times 0 squared plus 0 plus 1, the limit as x approaches 0 from the right. Is 1. The limit as x approaches 0 from the left of e of x equals the limit as x approaches 0 from the left of e to the 0, which is 1, f of 0, and I'm running out of room here, f of 0, we're going to use the bottom function because that's where x is equal to 0, so 9 times 0 squared plus 0 plus 1 equals 1. So, is f continuous? Yes, continuous, since f of 0 equals 1, the limit as x approaches 0 from the right equals 1, the limit as x approaches 0 from the left is 1, okay? All right, very good. So down here we'd have the same, right? You'd test f of 0. F of 0, you would use the top function, right? Because that's where x is equal to 0. So you get cosine of 0 plus 1, which is 2. So f of 0 is 2. The limit from the left is 2. The limit from the right is 2. Therefore, this function is continuous. Now, here's an example. Is this function continuous? So let's take a look. Let's try first. F of 1 equals negative 1 plus 2, which equals 1. So f of 1 is 1. The limit as x approaches 1 from the left is 3 times 1 minus 1. The limit as x approaches 1 from the left is 2. So therefore, the function is not continuous. Discontinuous, right? And we would say, since the limit as x approaches 1 from the left is not equal f of 1. Okay, so as long as you see two of them, if it doesn't, we don't have to check the limit as x approaches 1 from the right because we already know the limit from the left and the function value is not the same. Okay? All right, so I just wanted to give you some examples of continuous functions, okay? Polynomials, constant functions, the sine, the cosine, e to the x or a to the x, as long as a is positive, okay? So those are just some examples of continuous functions because if you graphed them, there wouldn't be any holes. Actually, we'll see why. So there are different types of discontinuity, okay? And we're going to look at these on a graph. So two distinctions, removable and non-removable. An example of a removable discontinuity is a hole. So remember, a hole is, the graph is going there, but, the function value doesn't exist at that point, okay? So there's a graph as an example, and we've seen tons of holes. But one thing we do want to distinguish is that at a hole, the limit from the left and the right are the same, but the function value is not the same, okay? So that's, if you saw in the test, that's sort of a distinguishing factor. You can have the limit from the left and the limit from the right at a hole, but the function's not, colored in, if you will. So f of whatever, say f of 4, right? We don't look at the hole for the value. We look at where the point is colored in, if you will, to find out what the function value is. Okay? So remember from our review at the beginning of the year and from last year, you find the hole algebraically by setting whatever factor cancels in the numerator denominator equal to 0. So in this example here, since they factored and got x plus 1 canceled out, you set that equal to 0, and that's where your hole is, okay? So for us, if we want to see if functions are continuous, and if the function's discontinuous, find the x-axis location of the discontinuity and classify it as removable or non-removable. Well, this function's continuous, right? Continuous since it's a polynomial function. Okay? If you type that into Desmos, just graph it, you'll see this, right? You'll see that, whatever number you plug in, there are no holes or asymptotes. Next one, we want to look, and there looks like there can be some factoring involved. So, if I factor the top, x plus 4x plus 1, and I factor the bottom, x plus 1, I set that equal to 0, and I get x equals negative 1, whole, and this is removable. Okay? So I have a removable discontinuity, okay, at x equals negative 1, which is really just a hole. All right, same thing here. So x minus 3, x minus 2, x minus 3. These cancel. So at x equals 3, I have a hole again, and the holes are removable discontinuities, okay? Why are they called removable? Well, let's go back up to the slide here. If we filled in a point, so since there's a hole right here, right, obviously, that causes problems. But we call it removable since, we can fill in a point here, right down here, okay? So we sort of it's almost like we took a point, we erased where the point is, right? Or we moved it, right? So let's say you have a grill, right? You have a grill and, you move it down here where this green dot is, and under the grill, a groundhog got in there, and if you fall in, you're going to break a leg or something like that, right? And it's sort of a goofy example, but anyways, so that's a removable. Now, you don't want to just assume that all rational functions have discontinuities, right? So this guy right here, if you're thinking back, you can't factor that guy. But if you remember from Algebra 2, you can use the discriminant of the quadratic formula to figure out if what kind of roots that the function would have. So the discriminant's less than 0, so you'd have imaginary roots. So there's no real number roots that make the bottom equal 0. So, only imaginary. So, this would actually be a continuous function. Okay? So there's no real number we can plug in the bottom that would make the denominator go to 0. So, therefore, it's continuous. Okay. All right. There's also non-removable continuities. These are called jumps and infinites. Okay? So a jump is where the limit from the left exists and a limit from the right exists, but they're not equal. Okay? Sometimes called step continuities, and you can see here, right, we go from up here, boop, and then you jump down to there, right? Or you start from the right and then you jump up. Okay? So we do see jump continuities with piecewise functions. So we won't really see these, but for example, if we take a problem I've already done, if we have f of x equals 3x minus 1 and negative x plus 2 for x greater than or equal to 1, okay, the limit from the left as x approaches 1 from the left is 2. The limit from the right, x approaches 1 from the right, is 1. So on a graph, right, if we have at 1, okay, and then f of 1 also equals 1. So at 1, there's going to be a point here. And you're going to have a graph coming down like that. But at the limit as x approaches 1 from the left goes to 2. So there's going to be a hole here. Okay, and it's going to be going like that. Okay, so that's what the graph would look like. So notice, f of 1 exists. The limit from the left exists. The limit from the right exists. But the limit from the left and right aren't the same. Okay. So I think looking at the graphs, those usually help. Okay. The last kind of discontinuity is infinite. Okay, that's where you have a vertical asymptote. All right, so that's where the limit from the left goes to infinity or negative infinity. The limit from the right goes to negative infinity or positive infinity. Okay. So again, an infinite discontinuity can be where we find the vertical asymptote, right? So after you factor and cancel, right, that's when you would set the denominator equal to 0, right? And again, we did do this, back in our review. So, if we want to find out if functions are continuous, obviously from a graph, you just look at where the asymptote is, okay? But for a function, if we want to find where the function is continuous, what we're going to do is we're going to factor, right, like we've been doing. So we have x over x times x minus 4. So, actually at x equals 0, there's a hole, right, and that's a removable discontinuity. But at x equals 4, right, we have a non-removable continuity, right, also called infinite, right? It's a vertical asymptote, all right? We could say infinite continuity, right? So, that's just an example. Here we have another polynomial function. So this is continuous. Down here, we don't have a hole because we can't cancel. So please don't do that. You can't do that, right? You cannot cancel. You can only cancel x's, if there's an x in every term in the numerator and denominator. So there's no hole, but there is at x equals negative 1. There's a non-removable discontinuity, right? So you could say infinite discontinuity, right, since there's a vertical asymptote. Okay? All right, so to summarize it, if a graph has a whole vertical asymptote or a jump, it's discontinuous, okay? If an equation has a whole or vertical asymptote, it's discontinuous, okay? Our removable discontinuities are holes. Non-removable discontinuities are jumps and vertical asymptotes, okay? And as we've seen, jump continuities algebraically are usually piecewise functions, okay? And again, we saw that equations can have both infinite and removable discontinuities. So I should say also, you can have a removable and a non-removable continuity at the same time. So, all right, so that's a summary, okay? So, you can write any questions that you have down. I'll make a question, and you can give me your 1 to 10 confidence scale.